I welcome you all for this presentation on satellite communication. So these are all the contents of my presentation: orbital perturbation, effects of non-spherical Earth, atmospheric drag, station keeping, and will be related to geostationary and non-geostationary orbits. First, you can start with orbital perturbation. So the Earth is considered to be a perfect sphere, and the force acting upon around the Earth is the centrifugal force. So he is considering the Earth, we are considering it as a perfect sphere, and the force acting upon the Earth is centrifugal force. Apart from this, the other forces also affect the motion of satellites. So these forces are the gravitational forces of Sun and Moon along with the atmospheric drag. So these are all the other forces affecting the motion of the satellite. One, it is the gravitational pull of the Sun. It also affects the movement of satellite around the Earth, and the gravitational force of Moon also affect the movement of the satellite, and also the atmospheric drag that also will affect the movement of the satellite. Actually, the effect of Sun and Moon is more on geostationary Earth satellites. So normally the gravitational forces of Sun and Moon is more on geostationary satellites, whereas the atmospheric drag effect is more for low Earth satellite orbits. So if the satellite is close to the Earth, it will be affected by the Earth's atmospheric drag, and if it is far away from the Earth, it will be affected by, or if it is in geostationary orbit, it will be affected by the Sun's and Moon's gravitational force. Next is the effect of non-spherical Earth. So ideally we are considering the Earth as Earth is having a considered as a perfect sphere, but actually the Earth's path is not a perfect sphere. So since it's not a perfect sphere, it causes some variation in the path followed by the satellites around the Earth. The Earth is bulging from the equatorial belt, and you have to keep in mind that an orbit is not a physical entity, and it forces results from a oblate Earth which act on the satellite produces a change in orbital parameter. So ideally we used to consider the Earth as a perfect sphere, but actually it's not a perfect sphere. So it will be bulging somewhere close to the equatorial belt. So it will produce a change in the orbital parameters. So this causes the satellite to drift from the actual position. So as this results of a regression of nodes and latitude of point of perigee. So everything will shift. So the change in orbital parameter will changes the satellite may be the regression of nodes and the latitude of the point of perigee. So this changes will leads to rotation of the line of apsides. So the orbital parameters will change because of this, because the Earth is not a exact sphere. As the orbit itself is moving with respect to the Earth, the resultant changes are seen in the value of argument of perigee and the right assertion of ascending nodes. Due to the non-spherical shape of Earth, one more effect called as the satellite graveyard is seen. The non-spherical leads to small value of eccentricity at the equatorial plane. This causes a gravity gradient on geosatellites and makes them drift to one of the two staple points which coincides with the minor axis of the equatorial ellipse. These are all the effects of the non-spherical Earth. That is, actually we are considering in our calculation path, we are considering Earth as a sphere, but actually the Earth is not a sphere. So there will be change in the Earth's parameter. So the change in parameter will leads to the actual location of the satellite in the orbit. Next, it is atmospheric drag. If this is applicable for low Earth orbiting satellites, the impact of this drag is maximum at the point of perigee. So at the point of perigee, it will be close to the Earth. So at this point, the atmospheric drag will be high, or it will be maximum. So simply dragging means pulling towards the Earth. Earth has an effect on the velocity of the satellite. So here, since the Earth is pulling the satellite, so its velocity will get reduced. So this causes the satellite to not reach the apogee height in successive revolution. So the influence of this atmospheric drag will pull the satellite from the actual apogee height. So this leads to change in value of semi-major axis and eccentricity. So actually, the satellite in services are moved by the Earth stations. Normally the Earth stations, they used to move those satellites back to their original orbital positions. So here actually, due to this Earth atmospheric drag, the satellites used to shift from their actual positions. So in Earth stations, they used to monitor this and they used to move back the satellites to the original orbital position. Next thing is station keeping. So the station keeping is important, that a geostationary satellite is to be kept in its correct orbital slots. So because of the influence of the gravitational pull, the pull of the sun and the moon, the satellite used to drift away from the geostationary orbit. So we have to put the orbit, or you have to continuously monitor the satellite position, and you have to correct it time to time. The equatorial ellipticity of the Earth causes the geostationary satellites to drift slowly along the orbit to these staple points, maybe to 75-degree elliptical and east and 105-degree west. So, these are all the two staple points. So, with these staple points you have to move back the satellites to the correct orbital slots. So, to counter this drift, what we have to do in Earth stations, we used to give an opposite directional velocity component to the satellite, and it will be done by means of jets which are pulsed once every 2 or 3 weeks. So, normally we will be having jets in satellites, and they will be used once in 2 or 3 weeks to put back the satellites in their actual orbital slot. These maneuvers are termed as east-west station keeping maneuvers. The satellites in the 6 or 4 gigahertz band must be kept within 0.1 degree of designated longitude, and in the 14 to 15 gigahertz band within the 0.05 degree longitude. So, this is the limit what you have to do. And in station keeping, what the people in the stations used to do is they have to use the jet in the satellite, and they have to move back the satellite, or they have to put the satellite in the correct orbital slot. Next, we can discuss about the geostationary and non-geostationary orbits, because we normally used to say about geostationary satellites and non-geostationary satellites. A geostationary orbit is one in which a satellite orbits the Earth at exactly the same speed as the Earth turns and at the same latitude, specifically 0, the latitude of the equator. So, this is the speciality of that particular orbit. A geostationary orbit is one in which a satellite orbits the Earth at exactly the same speed as the Earth turns. A satellite orbiting in a geostationary orbit appears to be hovered in the same spot in the sky and is directly over the same patch of ground at all time. So, for this purpose only, we are supposed to put the satellites in the particular geostationary orbit. If the satellite is in geostationary orbit, it means that it will come along the Earth with the same speed as the Earth rotates. A geosynchronous orbit, so is about geosynchronous orbit. It is orbit in which the satellite is synchronized with the Earth's rotation. So, actually in geosynchronous orbit, the satellite is synchronized with the Earth's rotation. So, a satellite in a geosynchronous orbit will wander up and down in latitude, although it will stay over the same line of longitude. The distance is about 35,786 kilometers, that is around 22,236 miles from the surface. This is about the geosynchronous orbit. So, it is around 35,786 kilometers. And the first geosynchronous satellite was orbited in the year 1963. Then about geostationary satellites, there are two kinds of man-made satellites. One kind of satellite orbits the Earth once or twice a day, and another kind is called a communication satellite, and it is parked in a stationary position around 22,300 miles above the equator of the stationary Earth. So, one kind of satellite orbits the Earth once or twice a day. So, they used to come around the Earth one or twice a day, but other time maybe the communication satellites are parked in the geostationary position above the equator of the stationary Earth. A type of orbiting satellite includes the space shuttle and the international space stations, which keep a low Earth orbit to avoid the deadly Van Allen radiation belt. The most prominent satellites in medium Earth orbits, that is MEO, are the satellites which comprises the Global Positioning System, GPS. So, normally we used to locate the GPS satellites in the medium Earth orbits, communication in the geostationary orbits. Thank you.